Okay, kids, we're back. Yes, we are. We're back and ready to do some physical grande. That's Portuguese for big physics. Okay, look it up. You don't believe me? Look it up. Okay, so today we're all about the moments of inertia. A moment of your time, please. Moment of inertia. This marker is dying. This marker is getting the axe, getting the 86. Okay, I'm gonna make that in. Oh, I'll show you some skill. Oh, nailed it. Skill. All right, let's try another one. Oh, let's go to a different marker. You know, we got a good camera here so you can see the different colors. Oh, we'll go orange. Yeah, there we go. Moment of inertia. Well, you know what inertia is. You know, I hope. It's something's resistance to change in motion. So everything has inertia. Nothing wants to. If you're not moving, you don't want to move. Thank you very much. Tell your friends, next show, 4 o'clock. Okay? Or if you are moving, you don't want to stop moving. I didn't want to stop. I just wanted to keep going out the door and down the stairs and to the truck so I can go home, have some dinner. Okay, but no, I'm back though. I'm back here for you. Okay, so inertia means you don't want to stop doing what you're doing. So we, the other day, were doing the great inertia race, and we had a ramp on a table. I didn't quite make it there, did I? Like that. Ramp on a table. And at the top of the ramp, we put different shapes, and we raced them. And we see who was the winner and who was the loser. Loser, L for love. Dodgeball 2005. Watch it. It's a great movie. So, some things lost the race because they didn't want to move as fast as something else. They didn't want. They had more not moving ability. Wait a minute. What? They had more I don't want to move than something else. If you have just a little bit of I don't want to move, or you have a lot of bit of I don't want to move, the lot of bit of I don't want to move isn't going to move as fast. I hope you're getting all this. So we would race a shape down. If the shape wins, like our steel ball, remember that? Don't mess with steel ball. That thing is like whoom, right down that ramp. So the steel ball versus, let's say, the roll of tape. Okay, the steel ball crushed the roll of tape. Well, why is that? Because the steel ball had less inertia or less resistance to moving. The tape had more inertia. It had more resistance to moving, therefore it took it a little bit longer to go, okay, fine, I'll move, okay? The steel ball's like, I want to move. So it wins. With me so far? When something is rotating, and all these objects were rotating, they were spinning about their axis, you call the resistance to rotate a moment of inertia. We talk about inertia with things that don't rotate. We talk about moments of inertia with things that do rotate. It means the same thing. It's just a resistance to motion, but with something rotating, we put the moment of in front of it, and we have something special, kids. Just like you and I, we have a special good time together. Special. Okay? You're all special. Yes, you are. Yes, you are. All right. Now, where are we? Okay, there are equations for moments of inertia. There are equations for them. For example, I don't want to give it all away because you kids want to look this stuff up on your own. Yes, you do. But anything with a moment of inertia will have an I, and an I is the moment of inertia equation for a rotating object. Everything gets an mr squared. It doesn't matter, big and little, whatever. You want to put big letters, little letters. You do whatever you want. Merc. Now, in front of that, we put a fraction. The fraction depends on what the shape is. Now, these equations are calculus derived, okay? Derive those using calculus, you know. Don't drive a car, drive calculus. So these are calculus, so we don't need to know how or why. We just need to know how to use them and what they mean. So I take any shape, if I have a particular shape, a derived equation, we'll use this and put a fraction here. Now, there are different fractions. 1/2, 2/5, 2/3. Okay, those are all diffractions for different shapes. I didn't tell you what they all were, did I? I'm not giving everything away. Okay, and there are some shapes that are so nasty high inertia that they have no fraction in front of it. They just I equals mr squared. Okay, that's a very large moment of inertia. If you have a fraction in front of it, 2/5, well, that'll only be 40% of mr squared. So that's lower moment of inertia, which means it would accelerate faster and move faster if we had the ramp down the ramp. Okay, is making some sense? So the higher the value for this, the more resistance you have to rolling, and you're going to lose the race because you didn't want to roll so fast. Okay, let me do an example problem with this. Now, an easy problem would be is calculate the moment of inertia of a disk. Okay, I'm giving one away, okay? I hope you appreciate this. A disk or a solid cylinder. A solid cylinder is the same thing as a disk. I know you might say, no, it's not. No, it's not. A disk would be like that wide, and a cylinder would be that wide. That's still a disk, not the same thing. They are the same thing. It's just that the disk is a fraction of the cylinder, and it's just a portion of it. So they are the same thing. They get the same equation, which is this one. So I gave one to you. Yes, I did. Okay, disk slash solid. Solid disk, solid makes a difference if it's not solid, or solid cylinder. Same equation. Okay, so if I wanted you just to calculate what the moment of inertia is of a solid disk that was had a radius of like 2 centimeters. Okay, it's like one of our weights in the back that we were rolling down, about 2 centimeter, a 0.02 meters. Okay, because you have to put it in meters. Then you put that diameter here, a radius here, and the mass. You'd have to mass it, and it's 100 grams. So put 0.1 kilograms here. Boom, easy peasy. Okay, that's so easy. A K person can do it. And the first several of our homework problems are like that. They're kind of level 1, level 2 problems. Forget that. You kids are smart kids. Okay, let's get right into a level 2 plus. Not a 3, but a 2 plus. This is a solid problem. Here we go. Solid problem for you. What if we wanted to calculate? I'm going to move a moment of inertia. Get rid of that. Make some room. We have a merry-go-round. Okay, a merry-go-round. And this merry-go-round, okay, looking from above, top view of my merry-go-round. Okay. And the merry-go-round has a radius of 2 meters. You know those push merry-go-rounds? Maybe you have never been on one. If you haven't had a childhood. Doggone it. Go out and find one, do it, and have a childhood. Okay, 2 meters, you push it around, you jump on. Okay, you grab the bar, you lean your head back off the side, and whack, it hits hits a rock as you're going around. Good times. Explains a lot too. All right, so now you have 2 meter radius, and let's put a couple of kids on the merry-go-round. We'll put a kid out here, maybe a kid opposite that. Doesn't have to be opposite, but we'll put them opposite one another. That kid here and a kid here. And we want to push this. We want to push the merry-go-round. So there's another person. Maybe you got good old dad out here pushing this thing around, and I get it to rotate. All right. Let's figure out how much torque, and it is a torque, that dad will be pushing on this with, and then from that, how much force. Torque, I thought that was last unit. It was, but it comes back to haunt us. Just like the kinematic equations, they never go away. It doesn't mean we can't go back and pick out and dip in and use old stuff. We can do that. So, and this is a torque. You're getting something to rotate. You're getting this merry-go-round to rotate, and you're applying force to the outside of it. Of course, you're going to push on a merry-go-round. You're going to push on the outside, right? That's torque. Okay, it's torque. You're applying a force 90 degrees to get something to rotate. Torque. So let's figure out how much torque that it would take to get this thing to rotate. Now, here's the conditions. So Dad starts pushing it from rest. Okay, so initial velocity. Now we're rotating this, so I'm going to use the correct symbols. So we have an initial velocity of 0. We get it going to a particular velocity, a final velocity of, let's say, let's go around 1, 2, all right, like 30 revolutions per minute, 30 RPM. And we do this in let's say 1 minute. So the time, let's push this faster. Let's get these kids have some fun, okay? So let's do this. We go from 0 to 30, and let's say with the time it takes me to accelerate is 10 seconds. Okay, so we go from start to 30 revolutions per minute in 10 seconds. And at that time, once we get up to this 30 revolutions per minute, then we stay at that velocity. Okay, so now we've got initial velocity, a final velocity, the time it takes to accelerate to this particular final velocity. Let's go ahead and calculate the torque that we need. Okay, now here's the thing. Here's a new equation for you. And the new equation, I took one of our equation sheets, okay, physics equation sheet, and I wrote it on here. Oh, I didn't write it on here. I circled it on here. It's written on here. And we will see that there are 2 torque equations. The one on the bottom is actually the one that we've used. We've used this one. Torque is equal to F times D. We're going to use this one. The one on top. Different torque equation. All right, this torque equation says torque is equal to I times alpha. That is a different torque equation. Now, if we do a unit analysis on it, we'll see it comes out to be the same darn thing as our old torque equation, which is F times D. It does come out to be Newton meters. Okay? Save that for a different time. You kids look it up on your own, but it does come out to be Newton meters. So this is just a different way to express torque. So what this is, remember I's? Moments of inertia and acceleration. Moment of inertia, acceleration. That is torque with a rotational sense to it. With just different units, we do come out to get Newton meters. All right, now, so let's take a look at this. What I need to do is calculate torque. Remember, that's one of the things here. Let's calculate the torque. So torque is equal to I times alpha. All right, let's plug it in and get her done. So torque is equal to I. Okay, I of what? What are we spinning around here? What are we spinning around? We're spinning around a merry-go-round. Now, if you think about it, what's the shape of a merry-go-round? I already gave you a hint because I gave you that moment of inertia earlier in the video. Yeah, it's a disc. It's a disc, okay, a solid disc that you're spinning around. So we're going to need the moment of inertia of the merry-go-round, which is a disc, which is 1/2, okay, mr squared. Capital letters, uppercase, lowercase, whatever. Now here's the thing though. You ready? You ready? Here's the thing. We have 2 kids, 2 noob sauces on this merry-go-round. And they are going, and their mass is toward the outside there. That's going to affect the spinach, okay? Put a little garlic on it. It's really tasty, spinach. These 2 kids on the merry-go-round add inertia. Now, if you think about it, you know that's true. You should know by now, I hope, the farther out mass is distributed from the center of rotation, think figure skater. The slower it rotates. But if we pull those arms in, if I'm a figure skater, so by putting mass of these 2 kids on the outside, we're adding inertia. We're adding resistance to speeding this thing up. Well, what do we do there? I mean, this is the disc by itself with no kids on it. That's the disc. What do I do to get the kids involved? We have to add their moments of inertia. But it's a kid. Yeah, they don't have any moments of inertia. Is there an equation for a kid? Yes and no. What we do is each child will have a moment of inertia of mr squared. And there are 2 of them. Can't you just say 2 mr squared? Yes, you can, but some of you are going to go scratch, scratch, scratch. Where'd you get the 2 mr squared? So we'll keep them separate. U and U. Why is it mr squared? Here's why. Listen. You're falling asleep after 15 minutes of video ed. Pay attention. Okay? This kid out here and this kid out here are spinning around on something which is spinning. What? They're spinning. Well, they're not spinning. They're on something which is spinning. So they're on an object which is spinning. So when you add mass to an object which is spinning, it gets an mr squared for its a moment of inertia. That's anything. So what if it was a cow out here? Would it get mr? Yes. What if it was a bicycle? Yes. What if it was a house? Yes. Anything that you add to something that's spinning has an mr squared addition to its inertia. Anything. Okay? All right, just go with it, okay? Go with it. So if I add anything to this thing which is rotating, it adds an mr squared to it. Now, this thing itself isn't rotating on its axis. The kid isn't rotating and spinning on its axis. They're just sitting on something which is spinning around. Mr squared. So this is the total amount of inertia for that rotation of that disk with these two kids on it. All right? All right. Now, in addition to that, we need the acceleration of the disk. We don't have that. We have the initial velocity, we have the final velocity, and we have how long it takes to happen. We got to calculate it. So acceleration is equal to change. I don't know what that was. I was like babbling. It was like talking in tongues or something. Divided by time. Now, the thing is, though, yeah, you see it, don't you? You see it, I hope. Revolutions per minute. 9! We need this bad Larry here in radians per second. So let's get that done. Revolutions. 1 revolution is equal to a new country. Bring the man down. 1 revolution. Funny. So 1 revolution is 2 pi radians. And then I'm running out of room here. Okay, I'm running into Mr. Kazura. Ang. That's Ang. See, there he is. Ang. Mr. Kazura's head, running into that. So times minutes. Over, I know I'm writing small here, minutes over seconds. Hope you can see that. 1 minute is 60 seconds. Okay, so let's get this into radians per second. So I made a conversion. 30 times 2 times pi times radian divided by 60. 30 divided by 60 is 0.5. Okay, so 0.5 multiplied by 2 is 1. So this comes out to be 1 pi radian. 1 pi radian. So now here's the thing. 1 pi radian, well, certainly I don't have to keep the 1 there. Just pi radians, right? So this is 60 divided by 60, so 1. It just drops out. So I get pi radians as my new velocity here, final velocity. Now, the thing is, though, physics does not like that pi thing. It does not like the pi thing, okay? It does not. So we got to put a number in for that. Well, let's just do 3.14, okay? 3.14. If you can, you'll write out, get pi, and maybe go out to the 782nd place if you want. You can do that. 3.14 radians. Wait. I'm putting that down here. I was running out of room. Put it here. So delta W, the change is 3.14 radians per second over 10 seconds. Okay, so wait a minute, what did you just do? Change, acceleration, change in velocity, 0 to 3.14, that's this velocity, so the change is 3.14. So 3.14 radians per second divided by 10 seconds will give me 0.314 radians per second squared. That is my acceleration in the correct units. Oh, man. So what do I do with that? Well, remember, this is torque equals moment of inertia times acceleration. So here's my moment of inertia, all those 3 things together, times acceleration, which we just calculated. That's acceleration here. So let's go ahead and start plugging stuff in and getting this problem solved. Okay, so let's get rid of this. Okay, so here we go. Torque is equal to 1/2 m. Now this is the mass. I need the mass of the merry-go-round. Now I never ended up saying that, so I'm going to have to make it up right now. Let's say the merry-go-round, big steel thick thing, maybe it's, I don't know, 500 kilograms. Maybe it's a 500 kilogram mass, big steel round, thick disc, 500 kilograms. And we said its radius is 2 meters. So that would be 2 squared. Okay. Plus the mass of the kid. This is the mass of each kid. And let's make it nice and easy here. We'll say each kid, nice little kid, oh, no, cute little kid. And maybe they're 20 kilograms each. Okay, they're twins, 20 kilograms each. So this kid here has a mass of 20 kilograms. And they're on the edge. You're going to sit on the edge of a merry-go-round. You're not going to sit in the middle. Don't be a wimp. That's wimpy people here. We want to sit out here and have fun. So you're on the edge. So that's 2. I'm a man on the edge. I'm a man on the edge. See? So 2 squared plus other kid, 20 times 2 squared. All of that multiplied by alpha, which we just calculated, 0.314. All right, do it. Okay, so this is going to be 4 times 500, or actually 2, because I got a half out in front of it. So 2 times 500 is 1,000. No, this one's dying on me too. All my markers. What's happening? What's happening, man? What's happening? Aliens, 1986, great movie. So this is 1,000. Okay. Let me double check that. 4 times 500. Yeah, it's 1,000. So this is 2 times 2 is 4. 4 times 20 is 80. Okay, and again, plus 80. 4 times 20 is 80. All right, all of that multiplied by 0.314. So T equals 1,160 times 0.314. And then finally, after all this time, and you kids all drooling because you're sleeping on me now, and finally we get the answer for what is the torque that it took this poor father, this poor dad, to push these 2 kids around under this velocity, getting this velocity in 10 seconds with this massive amount of stuff he's got to move. Okay, let's see how much force it took him. It's torque. We will have to figure out the force, but torque. All right, so torque is 1160 times 0.314, and that's 364, and we'll round it to 364 newtons. So the Newton meters. So it's 364 Newton meters of torque. That's the torque. 364 Newton meters of torque. That's the answer for that one. Oh man, we still have to do how much force? Oh my God, look at all that work just to find the torque. I don't want to do it anymore. I quit. I'm going to go to my guidance counselor and drop. I can't do this. We have got 95% of it done, people. That's the hard part. The easy part is this one. Okay, hang in there. You can do this. Hang in there. Do it. Take a break right now. Go take a... Oh, calm down and relax. Okay, feel better? Feel better? Good. Okay, so keep that in mind. I'm going to get rid of this. Make some room. Get rid of this. Making some room. Get rid of this. Clean that up. Okay, actually we can get rid of this all right now. We can get rid of that. Okay, so keep this. Now, this is one way to express torque. Okay, we call this rotational torque. Although torque has everything to rotate, but at least we say angular torque is a better way to say it. Angular torque. Rotational torque can be both. Both, what do you mean? Remember the other equation that we have for torque? Here's our old equation. And either one of these work. They both work. We can calculate how much torque or how much force dear old dad here is pushing around with either equation as long as he had the information to do so. So with this situation, given this information, to calculate the torque, we had to use this equation here because we had a particular shape we were moving around. But now, since these two torques end up being in the same place, we can calculate torque with either one. They're equal to each other. So that means this is equal to this. So I can say torque blue is equal to torque orange. And therefore, this is equal to this. So I times alpha is equal to F times D. And we just figured out the I times alpha. We got that. We have that. Yes, we do. Now do you see it? We have this. This is 260 or 364. This, we calculated, is 364 Newton meters. And we want to figure out the force. We just have to know the distance that dear old dad is pushing this around from the pivot point. Remember that pivot point. How far from the pivot point? That's the D. 2 meters. So I can solve for force. See, that was pretty easy. That was the easy part. Once we had the hard part done, the I times alpha, that was the hard part. Okay, 364. This part's easy peasy lemon. You thought it. You might have said it, but you thought it. You know. Squeezy. Yeah. So just take this and divide it by 2, and I'll get the force. So the force here would be equal to, that'd be 5, 6, 7, 8, 2. 182. 182 newtons of force. Okay, 182 newtons of force. Now remember I was saying, dear old dad, the poor guy, he's got to push with all this and it's just exhausting him. Actually, no, that's not a lot. He can do this. I'm trusting you. He can do this. There's no friction on this thing. Actually, no friction, let's say. A piece of cake. 182 newtons, that's like 40 pounds of force. You can push with 40 pounds. You could push 40 pounds. Okay? Yeah. Dad, what's he whining about? Don't be such a wimp. It's 40 pounds for crying out loud. So there we have it. There we have a sweet problem. That was a problem. It's like the most complicated problem you will get. The most complicated problem you will get with moments of inertia and torque of moments of inertia. All right? You can do that. You can do anything. Anything? Anything. Can I go to the moon and breathe without a space helmet? Well, no, you couldn't do that. You said any. Fine. You know what? Fine. You know what? That's it. I'm done. I'm out of here.